Okay. Wow, look at that. Audio is perfect the first time. Welcome. We have the final Lync session of the day, EXL 311, which is going to give you an overview of Microsoft Lync and what we call enterprise networking, or the network impacts. In this session, we'll kind of talk a little bit about some of the background of how we encode and decode packets on the network, and some of the changes we have with respect to support for networking topologies and components for Lync Server 2013. My name is Andrew Aronson. I am from Microsoft Consulting Services out of the Chicago area in the US, and I focus most of my time on Lync and Exchange technologies, helping customers plan and deploy those across the Americas region. So, since this is still beta content, all of this information, of course, is subject to change. We're giving you the guidance as we know it today. Of course, as the developers move towards a ship date, they may modify, delete, or add features that are not in this or that are in this content or not in this content. So please take everything with the caveat that session content is subject to change as we go move forward towards general availability of the product. The first part that we want to talk about is something we call packetization and sampling. For those of you who don't have a background on the concepts or what we're doing in terms of putting voice and video on a data network that we have. Traditionally, when we have a call established on the PSTN, going back years ago to when everything was what we call time division multiplex or TDM type networks, when an A party calls a B party, a signaling path occurs from that A party all the way to the B party. And as that signaling path moves across the public switch telephone network, we actually open or reserve a channel of bandwidth. Those channels are around 64 kilobits per second of bandwidth. By the time that signaling is complete to the B party, you have locked, essentially, a guaranteed channel or reserved a channel of bandwidth from the source all the way to the destination. That way we know when the B party picks up the handset, that audio can be transmitted back to the A party, and we have a guaranteed path for that audio to be consumed or to travel on the way back. We know the path. The path is guaranteed throughout the network. That is how the concept of TDM networking works. The downside of this approach is when there's silence, right, or there's no conversation, that bandwidth is still locked between the A and the B party. So this works very well for the concept of voice. It's been in production for almost 100 years essentially now. But over time, what we've seen is organizations move towards a data networking philosophy over the past 20 to 30 years, and then eventually start to put things like audio and video on that data network itself. The main difference on a data network is that we don't have that concept of a reservation or a guaranteed path from the source all the way to the target. We break up the data that needs to be transmitted, whether that's a file, right, an attachment, an email message, some stream of audio packets, for example, or whatever that source information is. We break it into packets and we drop it on the network. At that point, the network itself will manage the path from the source to the destination, and we might actually have some of the packets arriving in a different path or different, maybe out of sequence, for example, by the time they reach that destination environment or that destination node. So in the data network, we don't have that concept of a reservation. We just see packets being dropped on the network. They kind of flow. They find their own path throughout the environment. Some might actually get lost in transit, as we see some buffer overruns or busy or congested routers, for example. But in essence, most of those packets will make it there. If we have TCP, we'll retransmit the packets that were lost. If we're using UDP as a transport, those packets are forever gone, and we'll have to try to recreate at the destination side or request the information to be retransmitted as the information isn't there. So we see kind of two vastly different philosophies in terms to how to get that information from one side to the other side of the network. One side has a guaranteed path. The other side breaks the information up into small packets and lets the network itself figure it out. Question? Oh, thank you. Let's try that. My apologies. So, voice network side, right? Guaranteed path. Data network side, you're seeing the concept of packets distributed or flowed throughout. Thank you for that. Sorry, it shows up here, right? So I didn't look behind on the screen. In terms then of how to layer things like audio and video on a network, as organizations move to this data networking philosophy, primarily because of lower cost, you can get some very large bandwidth capabilities and you can merge a lot of traffic onto a data network. We have some interesting challenges then when it goes to putting audio and video. First of all, we have to make a decision of what codec to use. And a codec is essentially a way to take samples of voice or video, for example, and encapsulate that into different packets which can then be placed on the network. We also have questions around the network performance itself. Some networks are well designed and optimized, and so therefore there's very little packet loss, and ideally for locations that are close together, very little latency between them. Other networks are going to see a large amount of packet loss. We could see that, for example, on a congested network or possibly on wireless networks that we see deployed in organizations. And then finally, there's the concept of the media endpoints themselves. The media endpoints are responsible then for determining what the underlying network conditions are, and then using that information to make a choice on the codec that should be used, and or possibly to change that codec in flight. And so the Microsoft philosophy around this is that we can't always expect perfect network conditions. If we have them, that's excellent. We'll have some very clear audio quality. But if we don't have that perfect network conditions and an unmanaged network, for example, the internet, for example, we have to have a way to ensure that the endpoints are aware of this change or difference in network conditions and then can take some actions essentially to tune or adapt that voice or video stream that's being placed on the network in order to make those changes. Another aspect that comes into play is something called the packetization interval, which essentially is how much time do we wait before we capture a bit of that audio and then place it in the packet. For example, a common interval is around 20 milliseconds, right? And so this concept of a packetization interval comes into play because it affects the amount of bandwidth that's being used. And so with a traditional codec being developed maybe on the telecom side, there's the concept of all the packets will be the same size, and so therefore we have a very predictable rate of bandwidth on the network. And we know it's going to be 64 kilobits per second or 78 kilobits per second because we're taking these little sample sizes, we're dropping them into a packet, we're transmitting them across the network, and we're not making any changes to that codec in real time. The difference is if we do change this packetization interval, we'll see the bandwidth change as a result. And the reason for that is every one of these packets has the same amount of overhead. So an IP packet, for example, if you're using IP as a transport, has 58 bytes at the header, which is used for addressing information, maybe some DSCP markings, for example, and other portions there. That packet also has a payload, and if we're doing 20 millisecond sampling periods, that payload would be about 160 bytes if that codec is G711, for example. So as a result, the overall packet would be 160, right, plus 58, which allows us to calculate what an individual packet is. But if we want to calculate the overhead, we could say that in 1 second, with 20 millisecond sampling, we're going to get 50 packets in a second. And so if we know that we have 50 payloads, right, with 58 bytes of overhead, we know that the overhead with 20 millisecond sampling is around 23 kilobytes per second. So that gives us, we always know that whenever we're doing 20 millisecond sampling, the overhead just from the IP headers is going to be about 23 kilobits per second, right, above and beyond what we have in the payload. But if we change that packetization interval to 60 milliseconds, for example, now in 1 second, we only have 16 2/3 of a packet. So if we have 16 2/3 of a packet times the overhead of the IP header, or 58 bits, 8 bits per byte, our overhead just dropped to 7.7 kilobits per second. So we have a benefit to increasing the packetization interval, right? So obviously the longer we capture some of that audio before or the larger the payload size is, or the longer the packetization interval is, the lower the overhead required because we need fewer packets to arrive at the destination. So it would lead one to say, well, why not just increase that packetization to as much as possible, right? Therefore, more of the information being transmitted as payload, fewer of that, less data is being transmitted in terms of overhead, and so therefore we have a reduced network bandwidth impact for dropping this payload on the network. The reason we might want to change the packetization interval is because on a data network, the packets not only have a size impact, but we also have to worry about the packets getting lost. And so with a 20 millisecond packetization period, when we lose a packet, it's a very small sample size of that voice, and we could probably continue the conversation without that gap that might have occurred because we lost a little bit of the audio sample. As we increase the packetization interval, or increase the amount of time, or the larger payload type, more and more of that audio is going to potentially be lost each time we lose a packet. And so therefore, and the other side is going to sound a little bit with those gaps in the audio, right? You're hearing those gaps because those packets were lost because you had a congested network. You had wireless problems. Maybe you had someone doing a large file transfer, for example. But so therefore, there's a audio quality impact if we have a congested network and a large packetization interval period. Another way to look at this or to see how to show this is we have a sample here, right? Here's our audio wave kind of flowing throughout. We've broken this into five different packets. On a perfect network, all 5 of those packets will reach their endpoint unobstructed in the right sequence. We'll play it back, and we'll have the exact perfect audio recreated at the destination side. However, we're aware that not all networks are going to be a perfect network environment, right? We're often going to see some packet loss. And so when we have packet loss, we can do things such as 1, change the packetization interval, or 2, add technology such as forward error correction, or something we call FEC, to that packet distribution. FEC basically says that when we before we transmit the first packet, we'll wait actually to record the second packet as well and transmit 1 and 2 at the same time. Before we transmit 2, we'll transmit 2 and 3. And so we're actually doubling the payload on the network by adding or by transmitting, right, most of these packets twice over the network. But as a result, what we see is that even though in this case we had 50% packet loss, in reality, we only lost the third packet of voice because 2 was transmitted both on the 1-2 packet as well as on the 2-3 packet. 3 was transmitted on the 2-3 and the 3-4. Both of those are lost. But 4 was transmitted on the 3-4 and the 4-5. And so by adding a little bit of latency at the endpoint and at the source for, first of all, waiting to capture, and then second of all, waiting to get them back in, we're able to pull back additional audio information and play that back with just a single gap in the audio, which might be imperceptible to the end user. Additionally, we're actually able to take a look at and say, and extrapolate essentially what direction that wave or that audio was taking at the time that packet was lost, right? So rather than giving up all of that third packet that was lost, let's just take a look at where the audio was trending at the pickup and where 4 picked it up, and then try to guess a little bit of what that might have sounded like in the middle. This guessing, you'll kind of hear as a tinniness or a metallic sound often as you're hearing a voice over IP call. That's where that endpoint is trying to recreate some of the audio data that wasn't present in that initial packet. So sometimes you'll hear a little bit of that a different sounding voice, right? It usually comes across as metallic or a ring. I'll use the word metallica. The other word I'm thinking of is not coming to my head. But you've heard the difference in audio quality on that concept of a voice over IP call or a cell call, for example. So now we understand that the difficulty then, right, is we want to be able to do 2 things. The first priority is to ensure that the recipient has an audible audio conversation, right, so that the voice is transmitted in a way that the recipient can understand what that originator of the voice is saying. But we also have kind of a secondary goal, which is to try to help predict how much bandwidth that conversation is going to take on the network. What we wanted to show you those first couple slides for is due to the fact that we're making changes in real time. So in the Lync product, the endpoints are signaling to each other via the signaling path information about underlying network conditions. So we'll see things like jitter, packet loss, latency, right, that are occurring. And therefore, the source can then use that information to tune or add things like forward error correction during the call, or change the sampling size, for example, during the call, to try to increase the audio quality for the recipient. But as a result of this dynamic tuning or this dynamic shaping of the packets, what we see is that it becomes harder to predict with a degree of certainty what the bandwidth will be, because each one of these changes that we're making will dynamically change the bandwidth of the call. We can provide some averages or estimates of what that might be over a larger sample set, but for any individual sample, it becomes difficult to make that analysis and to guarantee that the bandwidth will be within a certain range or a certain threshold, for example. One of the big changes for Lync Server 2013 is around wireless, right? And so traditionally, we've been in a wired world. We've got one of the developers found a great shot of a wired up network closet with that mass cascade of wires attaching everything and connecting the components together. But we see more and more of the adoption of wireless, not just in terms of cell phones and mobile devices, but organizations are deploying wireless internally in their buildings so that employees can be mobile. They move around with their laptops or their tablets or phones, and they have that full network access inside of the network. With Lync 2010, we didn't actually call out and support media traffic over wireless or Wi-Fi type devices. We know that people used it. We wouldn't block that from occurring. But we didn't really have the capability at the time to ensure that you have a robust audio quality experience when using Wi-Fi as your transport medium versus a wired network. So our support statement said, best effort, right? We'll try to help you troubleshoot or diagnose audio quality problems. But if you have them, and it comes down to congestion at your Wi-Fi hotspot or some of the other issues that we'll talk about in a moment, we know that you'd have to take some steps to resolve that. One of those would be potentially, right, finding a network jack and plugging in. That being said, however, right, we also know that there were plenty of Lync 2010 deployments that work very well over wireless. And in the last couple of years, right, we have actually seen a spin-up of vendors who start to deploy advanced wireless technologies focused around things like audio and video to kind of enhance that quality of experience. And so with Lync 2013, we're now happy to announce that we officially support voice, or our media codecs essentially, over Wi-Fi networks as well as wireless networks. Part of that, right, is due to the fact that we're seeing this increased awareness by the Wi-Fi vendors to enable audio and video support, especially around things like WAS. Another one is we're well aware that there are mobile devices, right, tablets and phones, for example, or slates, that may only have a Wi-Fi connection. They're not going to have a cabled Ethernet connection. And so as a result, lack of support for Wi-Fi only device, or for wireless, would exclude some of these devices completely from our support statement. We do have a Wi-Fi deployment guidance white paper that kind of outlines a lot of the recommendations that we've learned both from our internal wireless deployments as well as from customers that have deployed wireless and have that ready for download, or targeting to have that ready for download and updated for 2013 around general availability. So the challenges, right, around wireless is, one, it's a shared medium, and not just a shared medium like Ethernet on a traditional hub, but we're not just sharing the bandwidth with other devices connected to that Wi-Fi hotspot, but we're also sharing that bandwidth with anything else causing electromagnetic interference, right? So that could be other cordless phones, Bluetooth devices, appliances, anything using that same wireless spectrum could cause some noise that's going to interfere with our client experience trying to connect to the hotspot. Initially, right, wireless was really developed as a kind of the data transport tool. So a lot of the first iterations of Wi-Fi didn't have the specifications or guidance to enable the vendors to deploy solutions that would meet real-time audio needs. Initially, it was, if you're refreshing a web page and that packet doesn't make it, it's TCP. You can re-request it. The server will resend it, and you'll get the information. We expect just some of that loss to be the case. And in a normal scenario, that's not that visible from an end user perspective. But when it comes down to the wireless and the media capabilities, right, that's obviously for real-time media capabilities, that's a different story. And so therefore, the industry has kind of worked around to develop some standards around being able to support real-time media flow over wireless. And then finally, there's differences around the mobility aspect. So if we have people who are using a tablet, a slate, or a laptop, they might have an excellent connection to their existing wireless access point, but then they start to move and become mobile. And when they move, we have to go and renegotiate, right, as that endpoint, let's say their laptop or tablet, moves to another access point. They eventually have to resubmit their credentials to authorize to that other point. Typically, in a Wi-Fi access point solution, that means providing like a WPA type, WPA2 type credentials, which means you're getting a token that's applicable for the existing access point you're going to. When you roam to the next access point, you're re-providing your credentials and getting another token specific to that access point. As a result, that little negotiation, right, could be 100, 200 milliseconds of delay. May not be noticeable from a media quality perspective, but if it starts to exceed those thresholds, that could be something that's causing that audio quality or audio degradation as those users move between locations. And surprisingly enough, one of the other areas that we find is around the concept of drivers. Surprisingly, drivers have a major impact on wireless performance. Drivers, for example, are doing scans periodically to see if there's any new wireless access points. Maybe one has a stronger signal, and I should reattach to that. For some drivers, that's every minute or two. They literally stop all broadcast and receiving of traffic and do a scan for another wireless access point. That could be anywhere from a few milliseconds to, again, half a millisecond or longer, which means that periodically your machine is literally disconnecting and reconnecting as it looks for additional wireless access point. So a poorly written driver, or a driver written in the legacy Wi-Fi world, right, where that momentary or temporary disruption of service wasn't noticeable, was tolerable. As we move towards the concept of putting real-time media flow, we're having to re-talk to those driver vendors to ensure that that connection process does something such as interleaving and doing it on a per-channel basis, not a full drop across all the transmission and receive of packets back to that wireless access point. In terms of wireless, we also have different deployment styles, right? So first of all, there's the concept of enterprise Wi-Fi deployments, which is typically the concept of some access points as well as controllers. Controllers will provide some capabilities such as once you do authenticate and get that key or token, let's spread that token or publish it to all of the wireless access points that are within the same zone. So maybe all the wireless access points in a building. That means that as your client roams, your existing key will be good for the other access points, and you won't need to go through that re-authentication or renegotiation process as you're roaming, which ensures that your call will stay up or your media flows up as you're roaming throughout the environment. Another one is around the types of radios or antennas, essentially, in the devices you're using to connect. A lot of the business class notebooks will use a 2x2x2 antenna, which gives a much stronger signal strength to the device that's coming down. A lot of the newer tablets as well have the concept of the 2x2x2s. But some of the consumer-grade laptops and notebooks, as well as typically mobile phones, for example, will use a one-way antenna and does not have the same signal strength and capacity as one that has the other, has more gain and has the ability to capture that signal in a more efficient manner. Also, we're starting to see, as we mentioned earlier, right, a lot of the enterprise-grade devices have the capability now to support wireless quality of service or wireless multimedia, essentially, which ensures that if your client is taking the packets with the correct DSCP markings, the access point will actually prioritize that traffic over other types of traffic reaching that wireless access point. For consumers, we also see a wide range here. One of our larger support issues internally is really around the concept of trying to ensure that people at home have a high-quality Lync experience. And it's actually led our internal support organization to provide a recommended list of wireless access points and routers due to the range of capabilities, signal strengths, and things like QAs that are available on these devices. Having a poor quality wireless access device, right, at someone's residence means that when they're joining or participating in a Lync call over wireless, they will have that poor audio quality experience, or maybe the recipients on that call have that poor audio quality experience, specifically just due to the user selection of what their home access point was. And then finally, there's the concept of hotspots. And with hotspots, right, kind of the public access point, it's really all bets are off. I mean, at this point, you're up to the whim of the person who's deployed that hotspot. Did they deploy one that has capabilities around WMM, for example? Is it overloaded with just too many public consumers? In those cases, your ability to have a strong signal, as well as the appropriate latency and bandwidth, is up to the capabilities of that hotspot. We see more of a user education issue. We can help manage your connection at work and possibly at home, but when you're in that public roaming scenario, it becomes a little more difficult for us to provide any class of service or guarantees from that perspective. The other area that we've done some changes to in Lync Server 2013 is around monitoring. And so we've had some capabilities around monitoring today with 2010 and prior versions, right? But with 2013, we've added some additional changes as well, even around the areas of System Center management. So first of all, we have, starting a couple releases ago, actually, with the System Center Operations Manager products, we had the product groups themselves write the management packs. So rather than the System Center folks trying to figure out what alerts, what events, what utilization levels of networking or processor or memory, for example, should trigger an alert, let the developers themselves identify what those alerts and triggers should be. And so as a result, the alerting and thresholds typically have some ranges, and we know whether you're in a green, yellow, or a red state, for example. But additionally, one of the main changes for 2013 is that we've had at your disposal the concept of the monitoring server role in Lync, or as we also call it, the call detail records. And so this server is capturing statistics on every call, every instant message, every screen share, every video call that's occurring in the organization, and a slew of metrics around those. And so you had some reporting capabilities in Lync Server 2010 to look at these and evaluate trends, kind of see usages, and use it to troubleshoot the environment. With Lync Server 2013, we're extending that to actually have System Center watching the call detail records environment and report on those trends or alert you in real time. So if you had a switch start to have bad ports or a wireless access point become overloaded, and calls all associated with that specific location, right, or a block of IP addresses start to have performance issues, you'll get an alert kind of isolating or pointing back to, hey, you've got a strong subset of calls over a certain link or in a certain location that are all starting to trend red, right? There's probably an underlying network issue there. Here's some information around contextual information that you can find in the reports to kind of see that data, and then use that to make some changes, either notifying the user, resolving the underlying problem, et cetera. But use the information essentially in the call detail records environment as a way to look at a real-time monitoring of your environment as well. We also have the concept, and we had mentioned in the architecture session around synthetic transactions. The change there for 2013 is that synthetic transactions now no longer have to be on the same subnet as your Lync server backend infrastructure. You can run those on the user subnets and or even externally on the internet, ensuring that you have you're capturing not just is the Lync server healthy, but is the network between users and the servers, or the network or the edge environment, for example, from the internet, healthy as well. For those QoE, or quality of experience metrics, we no longer have a dedicated monitoring server role, which was receiving the reports from Lync endpoints, such as soft phones, voice over IP phones, for example. They used to submit those call detail records post-call to the monitoring server. Monitoring server would store it into a backend SQL database. With Lync Server 2013 and the increased capabilities we have on the front-end server role, the endpoints submit that data to the front-end server role. The front-end server role will then store it in the call detail records database for SQL. Not just Lync clients and Lync phones, right? But also, as we can see, Exchange 2013, mediation servers, the AV MCUs, all of these Lync endpoints will report that data back, so you have a wealth of information in that call detail records or monitoring server database. If we look at some of the factors, right, that affect media quality at the network level, obviously the common ones around latency, packet loss, changing bandwidth conditions, potentially from wireless, right, or maybe a negotiation problem at a client that's wired. From devices, it could be anything from lighting in the area, right? Does the camera have the right capabilities or sensors in low light conditions? What about the ability of the device to isolate background sounds or keyboard clicks, for example. A lot of newer laptops have a way to sense when a key is being pressed and to remove that click from the microphone that's transmitting the audio back in. And so as the vendors increase the capability of their devices, the better that source capture of audio is, obviously the better it's going to be on the receiving side after we go through the decoding or the encoding and decoding of that over the network. And of course, environmental, the common ones are around noise. But now as we see more emphasis on video, lighting becomes important as well. So if you saw the demo in this morning's session, right, one of our folks joined but had the bright window behind him. All you see is a little black head kind of showing up in the video window. There's not much we can do on the Lync side to fix the environmental lighting that's in that location. The quality of experience and call detail records for Lync 2010. I'm just going to quick rapidly through here because these obviously are the same. We just want you to be aware of the wealth of detail that's being recorded, right? Not just information on the network itself, but is this TCP, UDP, IPv4, IPv6? Was it a USB headset? Was it a laptop microphone and speakers, right? For video, frame rates, quality, packet loss, forward error correction, all sorts of detail that you'll need to, or that you may need to analyze or update your network environment. For 2013 specifically, we've added some new capabilities. First ones are around multi-view and single-view video. We see a lot more data being captured in our call detail records from a video experience. This is to help understand what's occurring on each call. So when we do have reports of calls that are video calls, right, that have issues, we're able to actually look at that specific call in the database and see what was trending, what was occurring, did we have a codec change, was forward error correction turned on, for example, to help us understand what happened in that specific call. For audio, one of the big changes, we now have support for stereo audio, and so now we're capturing some of the stereo metrics in the call detail records for Lync 2013, as well as additional detail around some of the healer metrics. So when we saw that little extrapolation of the curve, right, for the audio wave flowing through, we're going to give you more detail about when we're trying to make those changes and what happened as a result and or why we had to make those changes to begin with, maybe due to jitter or packet loss or something else that was occurring. We're also seeing, right, one of the common scenarios for Lync is around application sharing. And so we've added metrics there, specifically around latency, some of the bursts. Application sharing by itself tends to be very bursty in traffic. So if we were sharing this presentation, for example, right now there's no information on the screen that's changing. But if I had one of those PowerPoint animations that breaks it into checkerboards and it rotates it and spins it through, we're changing potentially a 1900 by 1200 pixel display. Every one of those pixels over 2 or 3 seconds, that's a very, very large amount of traffic that would get sent over the network in a burst as that transition would occur flowing forward. We'll show you a couple samples of reports. So I spent a lot of time talking about the capabilities of the monitoring server and some of the statistics that we capture. But here's an example of how we use this for troubleshooting. So we have the default reporting view coming up here. We see the users going down to click on the media quality report. When we click on media quality, we're going to show you the numbers. But not only do we show the numbers, but we already know the thresholds of when a call starts to go yellow and when a call starts to go red. So as a result, rather than you having to kind of interpret the numbers and say, God, I can't remember, right? Is 4% jitter acceptable, or was it 9% jitter that's acceptable, for example? We'll highlight that information for you. Here we're showing that a lot of UC peer-to-peer calls, conference sessions, and other call types are all showing red for this specific set of calls. So clicking out that little plus, if you see the plus on the UC peer-to-peer calls there, will get us the actual subset of calls that were taking place. And we can see that some of those calls had no issues, whereas a subset of those calls had quite a few issues. We can see additional details, right? So we can see what the A party was using for a client, what the B party was using for a client. Was it communicator? Was it an IP phone, right? Was it the Mac Messenger, for example, in a couple of these cases? Here we can see when communicator was calling some of these other endpoints, we had a lot of inbound packet loss specifically in that scenario. So we know that the date and time of these calls, we can go back and work with the network team and say, hey, we saw a lot of packet loss during this time period for calls over a specific link or between two locations. Can we do some investigation maybe to see what was happening in this scenario? Here we show an example of one of the video reports, right? So we can see things here. Some of the new ones for 2013 would be the HD quality ratio, some of the forward error correction, and other characteristics or attributes of a video call that's being placed. In this case, it was an excellent call, right? We don't see any yellow or red highlights on that, so we know we had a high quality call for this specific endpoint. The next change that we're happy to announce for Lync Server 2013 is around IPv6 support. We had a lot of customers pushing us the last couple years, specifically in the Asia-Pacific region, around support for IPv6 and Microsoft Lync. We've got a subset of organizations now that are saying no new software or hardware gets deployed on the network unless that software or hardware is IPv6 capable. To explain, kind of justify why, right, we're showing the growth essentially in the people who use the internet or amount of the world's population, and we can see in 20 years, right, that 17 years there, we're going from 0 to about a third of the world's population registering or using devices on the internet. But the interesting one, right, is to show the IPv4 address blocks. Earlier, a few months back, we actually stopped, or the IANA has allocated the last blocks out to ISPs. And so in terms of availability for IPv4 addresses, there are none, right? So at the core addressing level, there are some ISPs that have IPv4 addresses. There will be no more granted out at the ISP level to provide those off to businesses, organizations, end users, for example. And there's no backup, right? This is a fixed addressing scheme developed over 30 years ago that's served us well, but as we see that explosive growth in terms of the internet population, we essentially are out of addresses. So about 15, 18 years ago, people understood that eventually we would reach this concept of IPv4 address depletion or exhaustion, and a few things sprang up. Some of them are methods to use technologies such as NAT or even carrier-grade NAT, right, to help address or mitigate the reduction or the eventual reduction of IPv4 addresses. The other is around a new protocol, right, so IPv6, and using that as the addressing scheme to provide enough addresses for the foreseeable future, at least another 30 years or so of growth in the internet, probably substantially more based on the amount of addresses available. I think the quote I heard is you could fit if for every area on the Earth's surface the size of a head of a pin, you could put 2 million IPv6 addresses. So essentially a very, very large number once we go to a larger addressing scheme that hopefully we would not exhaust and have enough without having to run out. So the problem, though, is some of these temporary workarounds, specifically things like carrier-grade NAT, right, have issues around media and audio quality. And so the preferred solution is not to use solutions such as NAT to work through IPv4, but literally to go transition to IPv6. One core prerequisite to that would be Microsoft adding support for IPv6 into the Lync product. It doesn't help us if you can deploy IPv6 in your organization, but Lync is not able to establish an audio call or a video call using pure native IPv6 addresses. And so looking at that, right, some goals for Lync essentially, well, first of all, we had a couple slides kind of walking through the transition technologies. IPv6, let me back up a little bit there. I thought I was out of order. Is not a protocol that can coexist with IPv4. So if I drop an IPv6 packet onto an IPv4 network, that packet is not going to be routed to the destination. The IPv4 devices do not understand IPv6. And same for IPv6 networks, right? If I drop an IPv4 packet onto an IPv6 network, it's not understood. It has a different addressing format. It's just something that's going to be discarded by those network devices. And so during this transition period where you're introducing IPv6, but you still have devices running IPv4, we have a requirement for what we call some transition technologies. And we've got a handful of these. One is called ISATAP, one that we use at Microsoft, right, which essentially allows IPv6 and IPv4 coexistence to occur on the network. Another one is called Teredo. That is something that can be used either on the internet or on the intranet. ISATAP is typically something that's deployed inside of an organization. Teredo is something that can be deployed for a home or end user who has both a IPv4, IPv6 address. They're going over the IPv4 internet backbone, but they want to use their IPv6 address, right, to get to an IPv6 website or endpoint at their destination. And finally, there's another one called 6-to-4. 6-to-4 is primarily used by mobile operators, and so we see this widely deployed in the telecom space as their backbones typically are around IPv6, but the devices themselves are often running IPv4 still as they make that transition over to IPv6. So we know, based on the background, right, that one, we need to have IPv6 support in the Lync product, and two, we'll need to be able to coexist for the short term or the interim period while organizations make the transition from IPv4 to IPv6. And so with Lync, our goals for adding IPv6 support were twofold. One, we want to be able to run IPv6 natively. So we don't want to add IPv6 support, but rely on one of these transition technologies in order for it to interoperate on your network. You should be able to run in pure IPv4, pure IPv6, or in a mixed environment, because we see Lync, our support statement for products is 10 years from the date of RTM. So that if we have RTM later this year, that would put support for Lync 2013 into 2012. Now, we understand that by the time 2012 comes around, we definitely will, or we expect to see organizations that would be pure IPv6, some sort of coexistence with IPv4, and we need to be able to support both of those end states during that time period. And so therefore, we want this both pure capability as well as this transitory capability built into Lync as we ship Lync Server 2013. So as we've added IPv6 support to Lync, we've had some questions as to how that support will work as we look at the different ways the Lync components interact. So one of them is at the signaling level. So first of all, right, client-to-server signaling has no preference. If you've got clients that are IPv6 and servers that are IPv6, we'll use IPv6. Clients that are IPv4 and servers that are IPv4, we'll use IPv4 for signaling. Server-to-server signaling, we actually prefer IPv4 over IPv6. Awareness there is just that we typically will see IPv4 still widely deployed. And also that we don't always see IPv6 networks have the same diligence or robustness in terms of routing. That actually leads into the next one around media. Same concept there. Typically, as organizations deploy IPv6, we find gaps or latency around routing that's just not, they haven't discovered yet because they don't have the wide deployment around the capabilities as they do with IPv4. The kind of the joke is, right, we've made a joke for years around Exchange, that Exchange was the world's best network analyzer. If you had a problem anywhere on the network, right, the first time you'd hear about it was someone calling in to say that their mail was down, they couldn't get to Outlook. But with a real-time protocol or communication systems like Lync, that's even more true. If we see those little blips or underlying problems on the network, it becomes visible very rapidly from the end user perspective. And so if we don't have a properly designed, with no gaps, right, on that IPv6 routing infrastructure, we will see loss of media or packet loss or degradation of service essentially at the end user perspective. And so from a media perspective, if we have both, we'll prefer IPv4. If you only have IPv6, we'll use IPv6, but if both of them are there, our assumption is that the network today is optimized for v4, and so therefore there's a preference around IPv4. Servers, we do have a setting in the central management store to allow you to enable and disable IPv6 support. Some people, even though we have support for it, there are some organizations that just want to turn it off until they've went through their planning and deployment for IPv6 as well. Once you configure that setting on the server, the media platform will honor it as well. So if we've disabled IPv6 for server-to-server communications, those servers are not going to respond to or transmit media that's being sent to them in an IPv6 platform. Clients, we don't have any preference when it comes to login and registration. We'll use either 4 or 6 at the end of the day. First one to respond, essentially. We'll send those out. And for media traffic, right, same concept as above. We prefer v4, primarily due to the fact that we assume that most organizations will have a more robust IPv4 infrastructure than an IPv6 infrastructure. Support and capabilities for IPv6, we listed them all here. So all of our core modalities or functionality in Lync, right? Voice, video, application, file transfer, all these will occur and will work in a pure or native IPv6 environment. When it comes to our PSTN/PBX/gateway process, we're working with the vendors right now to go through a certification to get them up to speed for IPv6. So we've modified our UCOIP, or Unified Communications Open Interoperability Program, to ensure that vendors have time to go through and update their products for that IPv6 support. Edge servers, audio, video, IM presence, ICE, done, turn, data collaboration, all those capabilities are there for IPv6. And all of our manageability tools, control panel, topology builder, right? You're able to enter both IPv4 and IPv6 addresses in. In the call detail records, quality of experience reports, same approach. If that call was occurring over IPv6, we will expose the IPv6 address information in those call detail records. We have a quick table here that shows the interop capabilities. So what we have is at the Lync 2013 level, right? So if we look at a Lync 2013 IPv6 only, Lync 2013 clients IPv6 only, we're going through to kind of validate. That's still in testing phase, but our goal is to have that fully supported. But when we look at down-level clients, right? So if we have a Lync 2010 client trying to go, which has only support for IPv4, trying to talk to a Lync server 2013 pure IPv6, obviously we're not going to get any capabilities in that scenario. If we have a dual stack client, we require a dual stack server infrastructure as well. So if we have IPv4 and 6 on our servers and clients, they will interoperate. If we have native, we expect native at both endpoints essentially for that interoperability to occur. The other areas, right, such as Exchange UM leverages UCMA. The UCMA version 3 in Lync Server 2013 supports IP version 6, and so therefore we have the capability or the support at the Exchange level to communicate with IPv6 back to Lync. Edge, as we mentioned, right, we have the capabilities as well for IPv4 and IPv6, as well as dual stack, so you can run both 4 and 6 addresses on your external edge interfaces and have clients connect in as long as those clients are dual stacked as well, as we pointed out in the previous. Same concept as we mentioned earlier around the PSTN, PBX gateway interop story. It'll take us some time to work with, they have to increase or add IPv6 support to their devices as well, but we've made the modifications in the testing program so that as they make those changes, they can resubmit them for certification, and we'll certify them for both v4 and v6 support. Final component, we talk about the concept of deploying Lync on a network. We mentioned earlier that Lync and the codecs essentially are written so that we'll support them on an unmanaged network, because we expect, in our sizing, typically we say approximately 30% of your users are outside of the organization at any given time, meaning they're coming in over the internet, and obviously we have no way to provide a guarantee or quality of service for an unmanaged internet connection. However, a lot of organizations have taken the time and done the due diligence to deploy technologies on their managed networks to optimize that call flow and media quality on the network. And that includes things such as DSCP. Would also include some technologies such as LLDP, or the Link Layer Discovery Protocol, and VLAN support. And the catch here, or the LLDP/VLAN, comes up in the realm of voice over IP phones. It doesn't necessarily apply to PCs. I'll come to that in a moment. But when we have a voice over IP phone, we have a decision point to make. Do we put the voice over IP phone on the same subnet as all of our end user workstations? Or do we have a separate logical subnet for those voice over IP phones that segregates that voice over IP traffic from our traditional data traffic? We support both approaches in Lync. It doesn't matter if that are the voice over IP phones for Lync or the Aries style phones will register whether they're on a dedicated voice over IP network or whether they're on a shared data network with other computers and workstations. If the devices, but this brings up a question. If we decide to deploy this dedicated VLAN for our devices, the device has to know somehow about that VLAN. We don't want to run 2 cables to every desktop. That would obviously reduce some of the cost savings, right? If we have to add network infrastructure in order to deploy voice over IP phones. So we want one cable running to the desktop, that cable going to the phone has a 2-port switch in it, and out of this second port, we extend that port over to the PC. But that means, however, that the device has to have some way of interrogating the network switch to say, what is the voice VLAN and how do I attach to it? There's a couple ways to do that. One of them is we support a technology called LLDP, or Link Layer Discovery Protocol, that as the phone is booting up and interrogating the switch, it will determine that, there is a voice VLAN capable. I should attach to VLAN 26. The phone switch port, the voice over IP phone switch port, will then request to join that appropriate voice VLAN. And at that point, voice traffic from the phone will go over the voice VLAN. Data traffic from the computer will flow over the data VLAN. And we've essentially isolated or segregated that traffic to provide possibly a higher quality of service on the VoIP traffic over the data traffic. There are some prereqs, right? The switch has to have some support for 802.1ab and the ANSI TIA 1057. But that's for switches that support LLDP. We can put Lync phones on those network devices, and they'll be able to interrogate properly and boot up on the appropriate voice VLAN. The other option for devices is to use DHCP. There's a DHCP options flag we can set, so the phone boots up on the data network. When it requests its DHCP address, it also requests a specific DHCP options ID, option 43, which allows it to determine is there a new voice VLAN, and if so, to reset, configure itself to join that voice VLAN, and then boot back up using the proper VLAN that it obtained from the DHCP server. The rationale around PCs is we don't have a way with Windows 7 and prior to segregate traffic leaving the PC with one network interface card to 2 separate VLANs. And so with a phone, we have a separate device. It can be on VLAN 26, PCs on VLAN 12. We have the capability for isolating traffic. But at the PC, we've got data and applications all going out a single NIC. One of the applications happens to be Lync, and there's no process for us to say, let's have the Lync traffic go out a separate dedicated VLAN and have the data traffic go out of a different data networking VLAN, for example. So when we look at stuff like LLDP and DHCP for VLAN support, this is really targeted around the Lync Phone Edition type of devices. Once the other network impact or area that we could take advantage of is something called DSCP, or Differentiated Services Code Point, also known as DiffServ. DSCP essentially is a way for packets to be tagged with additional information, specifically some information in the IP header, which denotes them to have different priorities. So we can assign expedited forwarding or assured forwarding or normal service. As a result of these packets being tagged, network infrastructure that's DSCP aware can then prioritize those assured forwarding or expedited forwarding packets over other packets that are on the network. So that ensures that we're less likely to have things such as jitter or packet loss for our voice or for our video calls, because those calls will have, those packets will essentially have priority. You could think of it as kind of the express lanes on the expressway, right? So as a result of tagging packets with DSCP markings, network infrastructure that's DSCP aware, users will have typically a better audio and or better video experience around that solution. We don't require it for Lync, but it's very common for us to go into organizations that have deployed another voice over IP system that may have required it. If that infrastructure is in place, we're more than happy to take advantage of it. There's a couple ways that we can mark those packets with Lync. With Windows 8, Windows 7, and Windows Vista, we actually have an Active Directory group policy that can specify a specific application that's allowed to tag packets. So in this case, we can tell group policy in AD that the Lync 2013 client application is allowed to mark packets with the appropriate expedited or assured forwarding. The reason we want to do this as a policy enforcement level is any technical user who might be aware that the network's using DSCP might want their machine to tag all their packets with expedited forwarding, right? That would give my machine slightly better performance than my neighbor's machines on the network because all of my packets would flow through and be okay. So as a result, we want to restrict that, usually via some policy setting. In some organizations, there's not a level of trust between the networking team and the Active Directory or Windows team, and so therefore the networking team wants to mark the packets themselves. And so there's two choices. One is you can allow the PC itself or the client application specifically, such as Lync, to mark those packets using an Active Directory group policy setting. The other is to go through, I think it's on the, here, is to have the client restrict the port range that it uses for audio and video traffic and have the network infrastructure identify that specific port range and then tag those packets as audio or video packets. And so with the port range option, we set a policy on the Lync servers and on the Lync clients to say all audio traffic will be within this specific port range. As a result, any packets that leave that PC or that server and talk to a switch or a router that's DSCP enabled, that switch or router can then tag the packets, and those packets will flow through the network with the appropriate DSCP taggings and DSCP priorities. In general, when we talk about the packet tagging like that, or packet tagging, we recommend that you make the client port range a subset of the server port range. It just makes it simpler for the network folks then to have a single port range that they're configuring rather than having two lines, one for servers and one for clients on all of those devices. If I back up a slide, I'll just show you before I flip through the, I know I flipped through it quickly. This one shows, for example, what the typical settings are for audio, for video, for signaling, app sharing, and file transfer around the which bit or which DSCP option to set on those specific packets. So audio, for example, typically will get expedited forwarding or DSCP 46, whereas video would get assured forwarding DSCP 34, which is slightly lower than audio, but more important than file transfer, for example, or file copies that are occurring. It's okay for a few packets to get lost in a file transfer. We can resubmit those. It just adds a couple of seconds to that overall file transfer to occur. But if we have audio, for example, that's being dropped right, that makes that conversation become unintelligible relatively quickly, and so therefore we want those audio packets to have some higher priority. So with that, we come down to the final slide. We have the related content slide for you. This points out all the different Lync sessions we presented here at TechEd New Zealand. These will be available for download and via recording within, I've been told, 1 to 2 weeks after the end of the session. It usually takes them about a week or two. Also in this case, this content is also hitting Australia next week, and the Australia folks want it to be fresh over there as well, so they were asking if it could be held back at least a week. And we said, well, it normally takes 7 to 14 days to publish, so I think you're in good shape. So thank you for coming out for the enterprise networking. We'll take some questions around that, or any other Lync 2013 questions you might have. So appreciate your time. I hope you guys have enjoyed TechEd so far, and we'll go ahead and, let's see. First of all, we got to bring up the random number generator. I really like this. It's so much easier than asking the question and trying to find out who was the first one to answer. So rand between 0, 3,000. Oh, we have 2. Excellent. So they will have 2 of them. The first number is 2021. We're within 3. 2018? We have a lucky winner. I don't see any other hands going up there. And our next random number generator will be and between 0, 3,000, 1,057. 1,009, we're within 48. 1,045, we're within 12. 1,046. That's what you get for being polite and letting him go first in the registration line. 1,046, we're within, that puts us within 11. Anyone up to 1,068? There we go. Thank you. So, sure can. Any questions on the networking capabilities? Wi-Fi, IPv6, DSCP, et cetera, et cetera? Yes. The question is the Lync phone support. It's 802.1e. Is that the? Oh, .1x. I don't know. That's one I'll write down. Hold on. I don't think so, but I will find out. I'll find that one out. Any other questions? And I'll try to find it right now, so you can. I'll ping some folks on IM in a one. Is there somebody right after me, Lohit, or do we have a few minutes? Do we know? Is it lunch now? Oh, so we have some time. I'll try to find that one for you right away.